You've likely seen this happen at the kitchen sink. Pure water splashes against thick grease, immediately beads up, and slides right off. The oil remains completely undisturbed. We are going to conduct a simple comparative experiment to observe exactly how soap breaks down that barrier, forcing oil and water to mix into a stable state known as an emulsion. By isolating this process in a controlled environment, we can see the specific molecular mechanics that make everyday cleaning possible. To perform the experiment, you will need 2 glass test tubes with tight rubber stoppers, a test tube rack, a beaker of tap water, cooking oil, liquid soap, pipettes, masking tape, and a marker. Step 1 is to take your tape and marker and clearly label your test tubes A and B. This ensures we don't mix them up once the process is underway. You also need to verify that your stoppers fit snugly into the tubes. We will be applying rigorous mechanical force in a moment, and a loose cap will result in a messy spell. Setting up these parameters carefully gives us a strictly controlled baseline, allowing us to accurately isolate the chemical reaction. Begin by pouring about 10 milliliters of water into both test tube A and test tube B. This gives us our starting volume. Next, take your pipette and carefully add exactly 1 drop of cooking oil to each tube. Be precise here. Adding too much oil will crowd the mixture and make the final reaction difficult to observe. Watch the physics at play the moment the oil strikes the surface. It instantly bounces back upward and floats, refusing to integrate. This happens because water molecules are highly attracted to each other, but inherently repel lipids. The water pushes the oil out of the way, forcing it to rest entirely on top. That stubborn boundary between the 2 liquids is the exact physical obstacle our experiment is designed to break down. Test tube A will serve as our scientific control. Leave it exactly as it is right now. To test tube B only, add a few drops of your liquid soap solution. This provides the chemical variable that separates our 2 samples. Now, insert the rubber stoppers into both test tubes and press them in tightly. Take 1 tube securely in your left hand, the other in your right, and shake them both vigorously at the exact same time. You must apply equal force for the exact same amount of time. Shaking 1 tube longer or harder than the other introduces a physical discrepancy that voids our control. By treating both tubes to identical mechanical agitation, we guarantee that any resulting difference between them is due purely to the addition of the soap. Stop shaking and return both tubes to the wooden rack. Leave them completely undisturbed and watch closely as the liquids begin to settle. In test tube A, the mechanical mixture is strictly temporary. The liquids separate rapidly, with the oil quickly gathering to float back to the top layer. Look at test tube B. The oil and water do not separate. Instead, they have transformed into a single, uniform, milky white liquid. Achieving this stable, cloudy state signifies the successful creation of a chemical emulsion. The question now is why the soap allowed test tube B to stay uniformly mixed, while the water alone in tube A separated immediately. The cloudiness you see is the result of light scattering off millions of microscopic structures called micelles that have just formed inside the liquid. This is a diagram showing a single soap molecule. Notice the 2-part anatomy. It resembles a tadpole, featuring a distinct round head on one end and a long wavy tail on the other. That wavy tail is hydrophobic, meaning it repels water. To escape the surrounding fluid, these tails aggressively embed themselves directly into the nearest drop of oil. Meanwhile, the round heads are hydrophilic, or water-loving. They point outward, interfacing comfortably with the surrounding water, and completely encasing the oil droplet inside a protective ring. These head groups are ionic, meaning they carry a negative electrical charge. Because every micelle in the tube is coated in this same negative charge, they physically repel one another as they drift through the water. This ion-ion repulsion permanently prevents the trapped oil droplets from clumping back together and floating back to the surface. The milky emulsion we see is simply millions of these microscopic cages, actively holding the oil evenly distributed throughout the water. By organizing these steps and introducing the correct chemical variable, you have engineered a stable emulsion right on your desktop. This exact molecular process happens every time you wash dirty dishes in the kitchen sink. The soap pulls the oil into micelles, lifts the thick grease away from the pan, and allows the water to carry it down the drain. Now that you have a working baseline, try resetting the experiment and introducing a new variable. Test what happens if you use warm water instead of cold and observe how temperature affects the speed of the reaction. Understanding this invisible chemistry gives us direct mastery over our physical materials, turning the impossible task of mixing oil and water into a routine we can repeat every single day.